Okay, I'd like to go over some more application problems of the natural law of growth and decay. That's the equation that I just erased. Um, so I'm going to re-plaster that equation back up here. Um, Again, like I said in the last video, it's one of the most important equations in all of math, science, and engineering. So it's not some random or tangential little item. It's a major um, major item. And again, it looks like this. And people may use different letters, and they may write it in a slightly different, with slightly different letters, but it's the same equation. E is always E. Remember, E is called the base of the natural logarithm. What were the key things, takeaway things I said about it? Number one, I didn't say where it came from, but it's approximately 2.71. It's an irrational number. It's named after the famous Swiss mathematician who was blind, Euler, Euler. And that letter is the letter that's used. It's used on your calculators, it's used in textbooks, it's used around the world. So that symbol we don't change. Um, I use T for time, but again, you could use any letter you want. And this, you see, there's some sort of standard traditional choices. This is a constant which determines how fast or how rapidly something is growing or decaying. But some people use C for constant, whatever. You can use alpha, you can use whatever you want. The capital A stand for amount. Remember, that's initial amount, that's ending amount. So let me do kind of a classic problem. This is a real world problem. Again, I'm not going to take the time, or I'm not going to, because you can go online, since you're online anyways, and you can find out as much as you want to know about radioactive decay right here on YouTube. Just type in radioactive decay, and you'll get at least glossy versions of what radioactive decay is. In the upper atmosphere, it would be nice if you had a periodic table in front of you, but in the upper atmosphere, there's so many things I'd like to assume maybe hopefully like what makes an atom a particular element. It's the number of protons, and nitrogen has 7. And up in the high upper atmosphere, every once in a while, a high energy electron, bing, smashes into a proton and creates a neutron. And to make a long story short, you get a radioactive isotope of carbon. It's called carbon-14. Carbon has 6 protons. Normally it has 6 neutrons, but this type of carbon has 8 neutrons. At any rate, it's carbon. You're made out of carbon. We're carbon-based creatures. Trees have a backbone of carbon. Fish have a backbone of carbon. Viruses and bacteria have a backbone of carbon. So that's why your life on Earth is carbon-based. And for carbon-14, the value of K, I just happen to know it's oddly easy to remember. But I'm not going to bother with the units right now because the units are kind of messy. So we'll ignore that for the time being. But the decay constant for carbon-14 is negative 0.0001. And I'm going to simplify things a little bit here. Carbon-14 dating is used to determine how old something is. And it won't tell you that the guy was murdered at 10 p.m. last Tuesday. But it could tell you if he was murdered 10 years ago or 1,000 years ago or 10,000 years ago. And there can be a fairly large degree of error on these measurements. What I'm about to do again, it's a little bit simplified, but the essence is still there. So let's suppose that in 1 cubic centimeter of, let's say, bone from a mammal, let's say normally there are 9 units of carbon-14. It's usually written like that. It's not an exponent, but whatever. But I'll just say it, carbon-14. Well, I'll go ahead and write it like that, carbon-14. You can make it a subscript or what have you, but the point is it's carbon and it has 2 extra neutrons compared to most carbon, and that renders it radioactive. Now, why am I saying units? A, I don't know what the value would be. And B, what scientists are really doing is they're looking at ratios of carbon-14 and its breakdown products. But so again, there's a lot I am just not going over. But the point is, as long as you eat and breathe, you're getting a fresh supply of carbon-14, as are plants and rats and birds and bacteria and fungi. But when you die, you stop getting this fresh supply of carbon-14 and it decays away. And let's suppose that some archaeologists dug these bones out of the ground and they measure that there's now 2 units per cubic centimeter of carbon-14. The question is, how old are the bones? And I'll show you how we're going to calculate that. We use this. This is a very good model for radioactive decay. It's extremely accurate. No scientific models are perfect, but some are very, very good, and this is a very, very good one. So at the end time, we had 2 units. At the beginning time, we started with 9. Easy, you don't change that, -0.0001. And the time we don't know, and we're going to solve for time. And just like on the last video, there is a very specific set of things you do to solve for an unknown when it's up in an exponent. So we'll divide both sides by this number in this place. In this case is 9. Once you do this 5 or 6 or a dozen times, you'll get the flow of it. It's always the same thing. We take the natural logarithm on both sides, as previously discussed, as written ln. And as I mentioned before, and I want to mention again, are you worried about this? No. How are you going to do this? You're not. Your calculator is. So this is not an issue for you whatsoever. The natural logarithm is an inverse function to e. They cancel each other out, so we have -0.0001 t. That's by definition. So, people wonder, well, where'd that go? Well, I talked about it in the last couple of videos, actually, last 2 videos, logarithms, exponents, or the exponential function. But it cancels this out, and then divide both sides by whatever this number is here. So we get t is equal to the natural logarithm of 2/9 divided by -0.0001. And you put that in your calculator and you get the answer. If I had to guess, I would say this is probably about 12,000 years, if I had to guess based on the numbers. But I can't be more accurate than that without actually putting this in a calculator. But we went over that last time, and I'll leave that to you. Again, just type that in a calculator. One other concept about radioactive decay, and then we'll move on to another example. And this is something you probably all heard of, and it's called a half-life. And there are half-lives to other things as well. I'm going to show you in other examples. But let's find out what the half-life is for carbon-14. The half-life is the amount of time it takes for half of what you started with to go away. When I say go away, because it could be through radioactive decay, or it could be through metabolism with drugs. I'm going to show you an example. Most drugs have a half-life. But what that would mean is, regardless of what you start off with, we're curious about when you have half that amount. So here, I can do this in general. Oftentimes people put a little subscript under t of 1/2, half-life. I've always favored using an h, but I really don't think I've seen anyone do that. So people usually put a little 1/2 in the half-life. Notice what happens. You divide both sides by a sub 0. And what this means is, for things that undergo exponential growth or decay, because quite frankly, I could have put 2 and that would have been the time. It's a doubling time. It's independent of how much you start off with. So it doesn't matter what you start with. It'll take the same amount of time to either double or cut that amount in half. And for that matter, third or quarter it. But people do use half-life as a standard reference point. So we have this. And let's take the natural logarithm on both sides and divide both sides by k, and we get kind of a relatively simple looking formula, and we get this right here. I divided by k, yeah. So it says if you have the decay constant, you take this. This is a number. Remember, you put this in your calculator. The natural logarithm of 1/2. You throw it in your calculator and divide it by k, the calculator, whatever it is, and then do this. With carbon-14, if you take this, if you take the natural logarithm of 1/2 and divide it by -0.0001, I think you get something like, it's 5,000 and some change, maybe 5,700 years. So every 5,000 or so year, well, it's not or so, it's an exact amount of time, but say every 5,700 years, you'll have half of what you started with. Okay, now, hopefully you read over the properties of logarithms in chapter 10. We wind up not using some of those properties very often. The rules or properties of exponents, yeah, we use them all the time. There's a couple we don't use too often, but there's a couple that we do. And let me show you one in particular that you want to make sure that you are aware of. If you have this, if you have the logarithm of something raised to a power, this power can hop down in front. I'm not going to bother proving this right now. It's not particularly difficult to prove, but it won't make you feel any better about it. So this is one property of logarithms that is used actually quite often. I haven't used it except I'm about to use it right now, and that's why I'm bringing it up. So let me show you. Suppose you have this as an answer, the natural logarithm of 1/2. Now remember, the natural logarithm is a logarithm where the base is e. So it's like any other logarithm. The base is e. We have a special shorthand way of writing this. I could write it like this. And you might wonder, why would you want to do that? And that's a perfectly good question. Some people would prefer to do that. And now I can use this property, and I can write this like this. Now, here's what you'll see. If you look up the concept of half-life in a textbook or online or wherever you look it up, that formula I had a minute ago, which I don't walk around remembering, but since I wrote it just a second ago, I do remember it. It was the natural logarithm of 1/2 divided by the decay constant. You will also see this written in textbooks as follows. You'll see it, the half-life is equal to the natural logarithm of 2, actually, sorry, the natural logarithm of 2 divided by the decay constant. And these two formulas are the same. That can certainly be confusing, because if you look at this natural logarithm of 1/2 and you compare it to negative natural logarithm of 2, they don't look the same, but they are in fact the same. Okay, let me do another example, not of radioactive decay, but I'm trying to think of my favorite examples here. Let's do, here's an interesting one. Bacteria in a petri dish. Now, the bacteria in the petri dish in question, we have to keep them happy. And I should say what I mean by that, but if you keep bacteria happy, they grow according to this. Now, in the real world, that always gets limited very quickly. The bacteria become unhappy. They become crowded. They're not very mobile, and so they tend to drown in their own effluents, their own waste products. But during an initial growth period, when they have food they need, and when they're not surrounded by toxic chemicals, they do multiply according to this equation. Or rather, more properly, this equation is a very accurate model of bacterial growth. But there are some constraints on this. So unlike radioactive decay, this definitely fails after a while. And I'll talk about that in an upcoming video, because we'll need a slightly more complicated equation to deal with that. Hey, rates of COVID growth have followed this. The percent of people in the population, or the numbers of people that have COVID, have followed a natural law of growth and decay up to this point. You can imagine it looks like this, but then it's going to level off, and it's going to follow what's usually called an S curve, or more formally, a logistics curve. And I am going to talk about that in an upcoming video. But let's suppose we have some bacteria. In fact, we count how many cells we have. And I just want to keep the numbers easy. So let's say we have 8 cells, and we let some time go by. Let's suppose we let 20 hours go by, and we count how many bacteria. And let's suppose we count that we have, I don't know, let's say 700. This is experimentally determined information. It's found empirically, so I have to give you this information. You can't theoretically derive this. But once you do this, and if you may, at least in theory, it's a relatively simple concept. In fact, laboratories, I think they still use this. It's pretty much, it probably should be put out to pasture. But what they would do is, hey, if you remember from your biology classes, or if you look through a microscope, most bacteria look the same. I mean, you have those names like bacillus and cocci and spiral, because at first people looked at bacteria and they said, well, this one looks round, that one looks like a tube, and this one looks like a little, I don't know, some sort of a spirally pasta. But other than that, they pretty much all look the same. So how do you tell one bacteria from another? And I'll show you, this was kind of a standard approach for decades and decades and decades. You look through the microscope and you just count how many bacteria you have, and you let some time go by and you count again. And from this, we can determine K. Now, in the case of bacteria, K is usually called the growth rate or something along those lines. But let's just say growth rate or growth factor, how fast the bacteria grow. Let's throw all this in here. And the amount at the end of the time is 700. And the amount at the beginning of the time was 8. E to the, we don't know K, but T was 20. Notice this is the exact same kind of equation. Exact same kind of equation. So we'll divide both sides by 8. I won't even bother to reduce because I see a calculator in our future, so I'm not going to bother reducing that right now. Although I'm tempted to, but anyway. Take the natural logarithm on both sides. Actually, I am going to reduce because if you're looking at a problem in a textbook, the textbook's always going to reduce that. So we'd have the natural logarithm of, say, 300. Oh, I could, wait a minute. I think 4, geez. 4, oh my gosh, I must be tired, huh? 4 goes into 8 twice. And 4 goes in there 175. That doesn't sound right to me. Oh, it is right, yeah. 4 times 100 is 400, 4 times 100 is 300. Okay, fine. So equals 20K. We'll divide both sides by 20. Okay, and this gives you the decay, or the, I'm doing bacteria in a petri dish, sorry. This gives you the growth rate for that particular bacteria. Now, in an upcoming video, I'm going to talk about, well, what about when the bacteria is not so happy? Because you can well imagine, you put some bacteria in a petri dish or in any finite, relatively contained environment, and pretty soon the bacteria is going to start crowding itself, or running out of food and drowning itself and its fellow neighbors in its toxic effluents. So it's waste products. This is a classic kind of problem. Then the other 2 examples I want to do in the next coming video are money in a bank. Or maybe I'll do more than that. I want to at least go over Moore's law for computing power, and how drugs are eliminated. We can model how the rate at which drugs are eliminated in the body. And so maybe we'll do those 3 examples, maybe more, but at least those 3 more examples in an upcoming video.